So in this problem, we have a skier who is pulled by a tow rope up a frictionless ski slope. The slope makes an angle 12 with the horizontal. Let's make a small sketch. The rope moves parallel to the slope with a constant speed of 1 meters per second. So the skier is being pulled with this rope, which is parallel to the slope. What other forces do we have here? It's a good idea to take a look at the other forces. One thing I know definitely there is a weight force and a normal force, so I can draw these. I have a downward weight and the normal. The surface is frictionless, so I will not draw a friction force. And these are basically all of the forces I have. The force of the rope does 900 joules of work on the skier as the skier moves a distance of 8 meters up the incline. So the work done by the tension is 900 joules for a distance d, which is equal to 8 meters. In part A, if the rope moved with a constant speed of 2 meters per second, how much work would the force of the rope do on the skier as the skier moved a distance of 8 meters up the incline? So we're told the rope moves with a speed 2 meters per second instead of 1 meter. Here, v was 1 meters per second. We're asked v equals 2 meters per second. What is the work done by the rope? So the distance is still 8 meters as well. Let's start by writing down the formula. The work done by the tension force is none other but the tension itself times d times cosine the angle between them. I can draw the distance d on my figure so I can see the angles. The skier is moved up the incline by a distance d equals 8 meters. So this is d. You can see that d is up the incline. The angle between d and t is obviously 0. So I will put here d cosine 0. Now, one thing I notice is if you look at the work done, it's independent of speed. Now, because it is independent of speed, I can deduce that the work done will be the same as the previous case when the speed was 1 meter per second. Now, you might think, what if when the speed was more, the tension was different? And that's a very valid argument. So if the speed is higher, can't I say the tension of the string is more? There's more pulling force. But the issue is, because v is constant, I can deduce that the acceleration is 0. And if the acceleration is 0, this means that F net is 0. Let's take that along the x-axis. This will give me that t minus w. Let's see the angle that w makes with the x-axis. This is going to be sine 12 equals 0. Then the tension equals w sine 12, which is also independent of speed, and the same in both situations, because in both situations, the rope is pulled at a constant speed, which means we have some equilibrium. We don't have any accelerated motion. So same tension, same distance covered, same angle, then the work is the same. So W equals 900 joules. This is the work done by the tension force. So one way to solve the question, which really doesn't work, is using the work energy theorem. And you might think of using this method because you saw the speed to be given. And then you would say, okay, in case one, V is 1 meter per second, so W net equals K final minus K initial. Here I have half m into 1 squared minus 0. And for W net, here is where the issue shows up. W net is not just the work done by the tension, it is actually the work done by the tension plus the work done by gravity plus the work done by the normal. So you really can't use this method unless you are able to find the work done by gravity and the work done by the normal, and then deduce WT from that, which is a harder method. It would work, so this method would work only if you pay attention that here we have W net, not just the work done by the tension force. The work energy theorem is for the net work done on the object, so you have to account for all of the forces. Cool. So essentially here I found the rate of the work by using W over T, the work done by the force, dividing by the duration of applying this force and doing this work. The duration here is different. When the rope is moving faster, then the duration is shorter. I found the duration using the formula for constant speed, which is V equals D over T. So I deduced T to be D over V. Shorter duration for the case where the speed is higher, and thus higher power is obtained when I am working through a faster work done. So we have a cabin in an elevator. It has a mass 3,000 kilograms and it moves. So I'll write the mass. It moves 210 meters up the shaft in 23 seconds at constant speed. So the distance is 210 meters. The time is 23 seconds and V is constant. At what average rate does the force from the cable do work on the cab? So we want the rate of doing the work, which is again the power. That's what we want. So I have written the power formula, which is W over T or F times V. This is a dot product, by the way. Looking at the given, I didn't really find the force. Maybe I can try to find it to reduce the work done and then find the power, or I can find the force itself and multiply by the speed. I don't have the speed, but it is easy to find. I have the distance and the time, so V is just D over T, which is 210 over 23. Let's calculate that. This will be 9.1 meters per second. So if I am to use this formula, what I still need is the force. We want the force from the cable. This is basically the tension force. Let's make a quick sketch. This is the cabin of the elevator, and we have an upward tension. What other forces do I have? I have a downward weight, and I can say that the weight is equal to the tension since F net is 0. Why? Because I have constant speed, so the acceleration must be 0. Always pay attention when you see the word constant speed. I recommend you immediately deduce and write down that A is 0 so that you are aware of it when you do problem solving. And then if F net is 0, then minus W plus T, I'll apply that along the Y direction, minus W plus T is 0, so W equals the tension. So, okay, I can deduce the tension force. It will be none other but M times G, which is around 30,000 newtons. Perfect, I can apply this here. The speed is 9.1, and this is a dot product, so it is basically FV cosine theta. Let's look at the angle between the tension and the distance covered, or the speed actually. The cabin is lifted up, so D is upwards, and T is also upwards, so the angle between them is 0. I can deduce the power. You should get around actually 10 here, 270,000 watts. This problem is on the work done by a spring. So I would like to just remind you the work done by a spring is equal to minus the change in potential energy, and this is basically half k x initial squared plus half k x minus half k x final squared. And if we were asked about the elastic potential energy of the spring, this is half kx squared. So it will depend on the actual compression at the point of interest. We will also study the work done by gravity and the gravitational potential energy. The gravitational potential energy is mgh, and the work done by gravity will be also minus mg delta h, which is, well, I can write it as mg into h initial minus h final. So, okay, what's the question? A 250-gram block is dropped onto a relaxed vertical spring that has a spring constant of 2.5 newtons per centimeter. So the mass is 250 grams. I'll convert that to kilograms. The spring constant K is 2.5 newtons per centimeter, which is actually 2.5 newtons over centimeter times 10 power minus 2 to make this in meters. So this is basically 250 Newton per meter. So the block compresses the spring 12 centimeters before momentarily stopping. This means that at this distance, X max, which is 12 centimeters or 0.12 meters, at this distance, we have V max is 0. What work is done on the block by the gravitational force on it? So I'll find the work done by gravity, which is mg into h initial minus h final. Now the initial height, let's see. Let's take the initial height to be here, just when the block touches the spring, and the final height, I'll take it here when the compression is 12 centimeters. So I can take my final point to be my initial height, my final point to be my zero height. Remember, when I study the heights, I need to choose my reference. So my reference, I need to select it. I like to take it to be the lowest point. So I'll take this to be the point where the height is 0, and I will equate that. So I will write down mg into h initial is 12 centimeters, and h final is 0. I have the mass. The mass is 0.25. This is 9.8. Can calculate this. Let me just check the final answer. 0.29 joules. So this is the work done by gravity, pretty easy. In part B, I want the work done by the spring, which we wrote as W equals half K x initial squared minus x final squared. I half K is 250. X initial is the initial compression. Again, I'm taking this to be my initial point and this to be my final point. At the initial point, there is no compression, so X is 0. At the final point, the spring has compressed by 0.12 meters. So I'll plug this in. I can calculate this. You will get minus 1.8 joules. This is the work done by the spring. In part C, we want the speed of the block just before it hits the spring. So what we're interested in is the speed here, which is V initial, according to my labeled points, all right? It's not the speed when the block was first dropped. No, it's the speed where it just starts touching the block. I want the speed of the block just before it hits the spring, so I want the speed here. By coincidence, I named this my point I, so I'll just look for the speed at this point I. How do I find this? I will use W net equals delta K. Why? Because I found the work done by gravity and the work done by the spring, and these are the only forces I have. There are no other forces. So W net will be WG plus W of the spring, and delta K is K final minus K initial. Now, K final is at my final point here, which is where the speed is maximum and the speed is 0 because the elongation or the compression is maximum. So K final is 0 and K initial is what I want. The work done by gravity is 0.29 and this is minus 1.8. Keep the signs when you add up the work done. If the work is negative, keep the sign preserved here. You will get V initial to be 2 into 0.29 minus 1.8 over the mass, which is 0.25 with a radical. We can calculate this. There's the M minus sign that I missed. You will get 3.5 meters per second. In part D, if the speed at impact is doubled, what is the maximum compression of the spring? So we're told V prime is 2V. So this is 2 times the 3.5, which is 7 meters per second. What is the work done? What is the maximum compression of the spring? So we want X max. So this is basically asking for this, for solving the problem all in reverse. I have reversed the whole thing rather than knowing X max and using it to find the work done by the spring and finding the work done by gravity and then deducing the speed from the work energy theorem. I will go the other way around. I will find the work done by the spring from the kinetic energy, from the work energy theorem. So I will deduce the work done by the spring from here. It will be minus Wg minus half mv initial prime. The work done by gravity does not change because gravity has covered. Actually, it does. All right. So we have a problem here. The work done by gravity will be different because it's a vertical spring and the compression is different. So the vertical distance covered, this one, it's no longer 12, it's something else. So I'll have to keep the work done by gravity in terms of this new distance. So this will be mg into the new height, which I'm looking for, minus 0. Here I have minus half times 0.25 times 7 squared. I have the new initial speed. The work done by the spring is going to be half times 250 into minus, okay, I named this h here. Let's name it x prime. Okay, it's not x, it's something vertical. I'll keep it as h. Whatever symbol you choose is totally fine. And h is what we have here as well. The compression of the spring is the same as the distance that the object covers, right? So I got this nice formula, which isn't really very nice because it will be a quadratic equation. I will get here minus 125 h squared plus 0.25. Okay, this will be 2.5 h equals, I'll calculate the right-hand side. This will be minus 6.125. So as you can see, this is a quadratic equation. You can solve it using the calculator or using the delta function, where you find delta and then deduce x1 and x2. I will solve this using the calculator. Let's see. You should get 0.23 meters. So in this question, we have a thin rod of length L equals 2 meters and negligible mass that can pivot about one end to rotate in a vertical circle. So this rod, like it has here some sort of an axis or a hinge, and thus it can rotate around this point in a vertical circle. A ball of mass 5 kilograms is attached to the other end. So let's just write the given down. I have the length is 2 meters. The mass of the ball is 5 kilograms. The rod is pulled aside to angle theta 0 equals 30 and released with initial velocity v0 equals 0. V0 equals 0, theta 0 is 30. As the ball descends to its lowest point, how much work does the gravitational force do on it? So we're interested in the work done by gravity, which is none other but minus mg delta h So this is mg h initial minus h final. Whenever I want to find the work done by gravity, it's a good idea to use a reference. So I'll take h initial to be 0 here. Well, this is not h initial. I'll name it h because this is h final in my study. This is the initial point and this is the final point. So I'll take the height to be 0 over here, which is none other but h final. So I'll have mg into h initial minus 0 here. I have the mass, but I don't have this height. This initial height, I don't know it. To find the initial height, I will use some trigonometry. Namely, I'm gonna look at the figure and choose a right triangle. Let's study this triangle here. This is a right triangle with a length L that I know over here and an angle that I know which is 30 here. I will deduce this length. I'll name it, let's name it L prime. L prime is none other but L cosine 30. Why? So in the triangle, cosine 30, which is adjacent over hypotenuse, is going to be L prime over L. So I can deduce that L prime is L cosine 30, which I can find. That's perfect. This will be 2 cosine 30. I can calculate that. Or let's leave them in terms of unknowns because it's interesting to see the relationship. So I found L prime. What I want is this height here. How can I find this height? This height is actually this whole length minus L prime. So one thing I notice is that this whole length here basically is L prime plus H. And this whole length here is actually the length of my pendulum. This thin rod will drop to this final point. So this is actually L. So I'll say here, but L equals L prime plus H initial, which I'm trying to find. So H initial is actually L minus L prime, which is L minus L cosine 30. I just found the initial height. This is a common problem in pendulums where we are interested in finding the initial height, and we use some geometry in order to deduce the initial height of the pendulum in terms of simply the angle by which we have lifted the pendulum. So I got this equation for H, and now basically the problem is solved. The work done by the gravity will be mgh initial, which is basically mg L into 1 minus cosine 30. This is basically 5 times 9.8 times 2 meters into 1 minus cosine 30. We find the work done by gravity. You will get 13.4 joules. Part B, what is the change in the gravitational potential energy of the system? This is very easy, really. One thing you can do is, if you are aware that the work done by gravity is just minus the change in potential energy, then delta U is just minus WG, which is minus 13.4 joules. I want you to always make a thoughtful examination of your results. We saw that from the initial to the final point, the work done by gravity is positive. This makes sense because the object is descending. So gravity supports this motion. Whenever you see an object descending, then gravity is supporting this kind of motion, and it will do positive work. Anything that is going upwards, the gravity will do negative work on it. It will resist the motion. And on the other hand, the change in potential energy is negative since h decreased and the potential energy depends on the height. Less height, less potential energy. So yeah, the potential energy has decreased. So always check that your values make sense. In part C, the gravitational potential energy is taken to be zero at the lowest point. What is its value as the ball is released? So I want U initial, basically. Well, I know delta U, which is U final minus U initial, is minus 13.4. Now, I took the final height to have a zero height, so this cancels out. So U initial is actually 13.4. And that's it. We found its value just when the ball was released. Do the magnitudes of the answers to A through C increase, decrease, or remain the same if the angle theta 0 is increased? So here my angle has changed and I want to see what happens. This is part D. So my angle has changed, then okay, let's look at the answers. H initial will be different. Namely, let's see, if I increase the angle, then the initial height should be more. You increase the angle here, cosine of the angle becomes less. So yeah, the initial height becomes more. If the initial height is more, then the work done is more. So theta 0 increases. I know the work done by 30 increases. And the change in delta U is going to be more than, and U initial will be more as well. And that makes sense. Like you increase the angle, then the initial height is more, and thus the gravitational potential energy, which is mgh, is also more. A 5-gram marble is fired vertically upwards using a spring gun. The spring must be compressed by 8 centimeters if the marble is to just reach the target 20 meters above the marble's position on the compressed spring. So we're told that there's a spring, and if that spring, let's draw the spring as its at its natural length, and then it is compressed with a marble by 8 centimeters, so that the maximum point, this is the final point, will be 20 meters above the marble's position on the compressed spring. So this is 20 meters above. What is the change, delta U, in the gravitational potential energy of the marble Earth system during the 20-meter ascent? That's a nice question, pretty easy. I want the change in the gravitational potential energy. This is U final minus U initial. I always like to take the lowest point to be the point where the height is 0. You can take the height to be 0 at the final point, and then you would get negative height here at the initial point. Or you can take the height to be 0 when the spring was relaxed, and then this will be negative, this will be positive. To me, I find the easiest study is when I look at the lowest point in the whole figure and take that the height to be 0, and then everything else will be positive as well. So If this is my reference for the height, then U initial is 0, and U final is mgh, which is, let's see, I have the mass, 5 times 10 power minus 3, g is 9.8, and the height is 20 meters. So we can calculate UG. This is easy. This will be 0.98 joules. So I found the change in the gravitational potential energy. In part B, I want the change in the elastic potential energy of the spring during its launch of the marble. So I want delta U elastic, or delta U of the spring. One thing I want to see is, let's see, I can write this as half kx final squared minus half kx initial squared. But I have one problem, which is that I don't have k. So one thing I can do is, well, one nice thing I can do is I can think of W net equals delta K and try to find the work done by the spring and deduce the change in the potential energy of the spring. But I need points where I know the velocities. What I will do is, I know that here at the initial point, at the maximum compression, at H initial, we have maximum compression. Then V initial is 0. The marble was at rest. Also, at H final, this is the maximum height. So V final is also 0. That's perfect, because now I can write W net to be equal to 0 between the initial and final points. And W net is basically the work done by gravity plus the work done by the spring force. The work done by gravity is from this 0 height to the 20-meter height. It's none other but minus the change in the potential energy here. Means I deleted my notes by mistake. It's okay. I'll just continue with my results. So we found the UG to be 0.98 joules. And I'm trying to find the change delta US. And I'm using W net equals delta K. W net is the work done by gravity plus the work done by the spring force, and delta K is 0, as we discussed. The work done by gravity is minus the change in gravitational potential energy, and the work done by the spring is minus the change in the potential energy of the spring. And this is what we want, basically. It's going to be minus delta UG, which is very nice. This is 0. So minus delta UG, which is minus 0.98 joules. Let's look at the work done by the spring. It is negative, and this makes sense because the object is ascending upwards. Okay, let's look at part C. Now we want the spring constant. That's pretty easy. I found the change in the potential energy of the spring to be minus 0.98, and this is also equal to, okay, that's so annoying today, sorry about that. So we found the delta US to be minus 0.98 joules, and what I want is K. Delta US is equal to the initial minus the final. I'll just stop using the slideshow to avoid this from happening again. All right. So delta U for the spring is minus 0.98 joules, and this is equal to half K x final squared minus x initial squared. The final compression of the spring is 0, and the initial compression is this 8 centimeter here. So this is 0.08 squared, and K is, let's see, K is what I want. I have 0.5 here, and delta US, as you saw, is minus 0.98. I'll just rearrange for K, and you will get 310 newtons per meters.